So I'm going to talk about uncertainty quantification in complex models from a statistical perspective. So uncertainty quantification in general. Everyone goes on about big data and the use of algorithms in inverted commas in public life. But at the same time, there's actually been a big rise in the use of numerical models where we solve ordinary differential equations and partial differential equations, and that's not as remarked upon, but it is happening at the same time. So whereas people used to design cars by putting them in wind tunnels, they now put them in silicon wind tunnels inside a computer, and they solve differential equations. And I've probably not turned the microphone on. Yeah, okay. So they solve partial differential equations and ordinary differential equations for various things where we didn't do it before. And that's even getting into the social sciences. We had a workshop a few weeks ago where we had a very interesting talk about demography and the use of equations like this in demography and of uncertainty quantification. So these equations are almost always deterministic, but they're uncertain. They're uncertain because there are unknown parameters within the equations themselves. They have unknown boundary conditions and initial conditions. So although the equation itself, you put the same numbers in, you get the same numbers out, is deterministic, but these other causes of uncertainty mean we don't know what the true, in inverted commas, answer is. And the other one we need to worry about is these equations are not a perfect picture of the real world. The real world is not a set of partial differential equations, it's something else, and there's missing bits. And some of those missing bits we know about, and some of those missing bits we don't know about. All that means that a prediction from a deterministic set of equations, whether it's the response of an aircraft or the weather tomorrow, has uncertainty on it. Now that uncertainty varies from case to case, and it's a lot higher in what the weather is tomorrow than the response of an aircraft, but the same principle holds. So this program talks about complex numerical models. And what's my definition of a complex numerical model? Well, in this context, I would say it's one that's so computationally expensive you can't afford to solve these problems by Monte Carlo methods. So by Monte Carlo methods, I mean that you sample from some input x here, and you put it through my very complicated model here, y plus cos 2x. And I sample here, and it has a nice normal distribution, and I build up the distribution here. But you can see, even though I've got a nice sample from the normal distribution, this is pretty ropey at this point. You need a lot of Monte Carlo samples to get a good distribution of the output. And if the model's expensive, you can't afford to do that. It's also not a terribly sensible thing to do. But it's the naive baseline, what you might do if you didn't think about the problem. This is one of the interesting things about this problem is that different approaches have arisen in different mathematical communities. So the applied maths numerical analysis community have looked at, or are still looking at, a careful analysis of the numerical versus the analytical solutions of the PDEs and the ODEs. So the equations we write down are infinite dimensional. They have continuous functions in them. We can't solve those apart from in a few specialized instances. And we produce numerical solutions to those in the computer, and those solutions are not the true solution. And there are a lot of very clever methods that have been developed to actually look at what those errors are, and Catherine's going to be talking about some of those in the next talk. Now, the other community that's looked at this is the statistics community, and we take a very different approach. Most statisticians are not very good at solving partial differential equations, so we don't. We treat the model as a black box. It's a piece of computer code that someone gives me, and I run it, or in lots of cases, I tell people where to run it because it has to go on their supercomputer because I don't have a supercomputer. And I run a certain set of inputs, and I get outputs, and I look at the relationship between those two, and I infer the properties of what's happening in the black box purely from the data that I get. Now, those are very different approaches. This program at the INI is all about bringing those two communities together, and so far I can say that's been a very, well, I found it a very fruitful thing to learn about how applied mathematicians do this part, and I hope they're finding it interesting to find out about how I do this part, and we're coming up with some interesting new ideas and ways of tackling this. But I'm going to talk about the statistical approach. So we treat the numerical model, as I said, as a black box. Don't know what happens inside it. To some extent, I don't care what happens inside it. And I generate a well-designed training set of model, and I'm going to stop calling this a model. I'm going to call this a simulator, because I'm going to have models of the model, and it gets confusing if you don't make that distinction. But at some point I'll probably call it a model, but I'll try to call it a simulator. So the black box is a simulator. It's a simulator of some real-world process. So I generate a well-designed set of training set, and then I build a statistical model of the relationship between the inputs to that model and the outputs to that model. I model the model. And this statistical model is known as an emulator. Some literatures call it a surrogate or a meta-model. They're all the same thing. They're fast statistical approximations to the full numerical code. Now, little diversion. This model that's a black box is normally a set of partial differential equations or ordinary differential equations. It actually doesn't have to be. It's just some big computer code. It could be something that's come out of some weird machine learning algorithm, and we could still learn about it. But in general, and what we're talking about in this program, you can think of this as a big set of partial differential equations or ordinary differential equations. But it's slightly broader than that. So we want to model the model, and there are a number of ways you could do that, but in general we use a thing called the Gaussian process. So the Gaussian process is a stochastic process, and it's the equivalent of a normal distribution but for functions. So rather than just getting a distribution of numbers, I have a distribution of smooth functions. And it's defined in the way that a normal distribution is defined by a mean and a variance, or for a multivariate normal, a mean and a covariance matrix. This is defined by a mean function, and conventionally we take that as the sum of a set of basis functions with some unknown parameters here. We don't have to, but it makes life so much easier, we always do. And a covariance function, which gives you the covariance between a point here and a point here. So how are those 2 points connected? There's the mean that gives you the sort of deterministic connection between them, and there's the probabilistic connection between these two that's given by that covariance function. And all marginal and conditional distributions are normal. So every time we take a sample from this thing, it has a normal distribution. Now, because we work in computers, we can't actually have distributions of functions. We can have those in mathematics. But in the same way we can't solve the PDEs analytically, we can't actually get hold of a Gaussian process and simulate from it. We can only simulate points from it. So let's see a Gaussian process in practice. There's a nonlinear function. That's my well-designed training set of model runs. And I now take away that function. And I've only got these 4 points. And I fit my Gaussian process. So my Gaussian process is a stochastic thing. This is the mean of that Gaussian process. Goes through the points, exactly interpolates. And it has some uncertainty. And here I've put plus or minus 2 standard deviations, approximately 95%, around the mean. And if I put the original function back, you can see it's doing a good job. This way of plotting it, where I've put the point and I've drawn basically the marginal distribution at each point, is a little misleading because everything is correlated. Nothing's independent. Everything is correlated because I should probably take draws from this distribution and plot the lines which are the different functions that the Gaussian process produces, but I don't have a graphic that does that. But these things are all correlated. So a point, if I draw a point here, it's related to the point next to it because it's a continuous function. It's important to remember that everything is correlated in what we're doing. So Gaussian processes exactly interpolate the data. And lots of time that's what we want. We're running a deterministic model that tells me the strength of an iron bar. Well, I want my statistical model to reproduce that. So it's a good thing that it interpolates. But sometimes I don't want it to do that for various reasons. And we can get around that by adding a white noise term, a simple uncorrelated random piece, which is known as a nugget, which goes back to the history of spatial statistics in the mining industry in South Africa, and we're stuck with the name. So a nugget is just a little bit of random noise that we add everywhere. If you add that little bit of random noise, then it doesn't interpolate anymore because it's got this extra bit of noise on top of it. Why might you do that? It helps with numerical stability. There are other ways to solve the problems with numerical stability, so that's probably, it's a little bit of a cop-out. It's the easiest way to get numerical stability, but it isn't terribly mathematically sound. A more important reason for using a nugget is that sometimes we have an awful lot of inputs. We often have an awful lot of inputs, and we want some of them. They don't do much, but they do something. So we say, we don't care about these. We're not going to model with them in our Gaussian process. We're just going to treat those as random. They add variance, but they don't actually change the deterministic thing. So we add them as none, and that would give us a nugget term here. So if you see people talking about nuggets, they're either doing it for numerical stability or for this rather more principled reason of explaining some of the inputs in a way that matters. So we've got Gaussian processes. Now we want to build a Gaussian process emulator. We use a Bayesian approach. So we have a prior form for that mean function. We might say, well, we're going to have a linear mean function, or we could make it quite a complex polynomial or a Fourier or a wavelet sequence. It doesn't matter. That's tailored to the problem. We specify some form of the covariance function. This one's the most popular, though it's a little controversial. The advantage of this squared. Exponential covariance function is that the draws from the Gaussian process have all their derivatives. They're very nice and smooth, but sometimes they're too smooth. And there are other covariance functions that don't have that property and are less smooth, and we argue about those, but that's an argument for another day. We put priors on the hyperparameters, so the hyperparameters are the betas that sit in here we saw before. This delta, which is the length scale, how wiggly the lines are going to be, and this sigma squared, which is how big the Gaussian process is allowed to go away from the mean. We often put non-informative priors on these, but again, we don't have to. If we know something about them, we can include that information. And then the emulator is made up of the Gaussian process, the prior specification, and that training set. And those create the emulator. So the emulator isn't just the Gaussian process, it's the full set of things. Now I said we did a well-designed experiment. And this is a vital part of the process. So I often talk to scientists and sometimes people from the private sector who want to fit an emulator to their data, and they say, oh, I've done lots of model runs. And I say, well, to be honest, you've probably not done them in the right place. We have a particular reason for putting runs in particular places. People who just do them usually just run them around where they expect the answer to be. But we want to model the model behavior everywhere. So we often, well, always want something that's space filling. We want to fill space so that we can tell you what your model is going to do everywhere and gain information from there. And I'll put some alphabet soup up here. Latin hypercubes are probably the most popular way of designing experiments, and I'll show a Latin hypercube in a minute. But people also use things like quasi-Monte Carlo to fill space with as few points as possible. What's becoming more and more popular is what's called sequential design. So we fill space, spend some of our computer budget filling space, and then we target points according to where we want to learn. That's the space filling design. That's a maxi-min Latin hypercube, 25 points. The Latin hypercube means that the 25 points, if you divide this up into 25 regions, there's 1 point in each region, and there's 1 point in each region along here. So the margins are covered densely. Now we can't afford to have 25 by 25 points. That's an awful lot of points. I'm only going to have 25 points total. So we scatter them around. We randomize them. And in this case, it's not just a Latin hypercube. It's what's called a maxi-min Latin hypercube. And we've taken lots of Latin hypercubes, and we've chosen the one where the minimum distance between points, and I think that's here, has been maximized. We've pushed points apart. So we've tried to cover space as evenly as possible, as cheaply as possible. Now we don't have an optimal maxi-min Latin hypercube. We just sample 1,000 and choose the best one. If anyone knows how to do the optimal maxi-min Latin hypercube, I'd like to know. No one does. That's the sort of design we start with. It's important to get it good, it's not important for it to be optimal. So we take that training set, we build our Gaussian process emulator, and now we have to validate it. I always tell my students it's really easy to build bad emulators, it's quite hard to build good ones. So we check that the emulator is correct. So we might do, the most popular way is to leave one out validation. So if I go back to this, we would go through each point in turn. So I take this point, I'd remove that point from the calculations, build the emulator on the rest of the points, and predict what that point is. I know the true answer there, so I can measure how well I'm doing. And if I don't predict in a probabilistic sense correctly here, so I don't have the correct number outside those confidence intervals, so we should have 2.5% above and 2.5% below, then I would reject that emulator and I'd go away and rebuild it. I might do some more model runs. I might change that covariance function. I might change the prior mean function. The other way to do the validation, which is a better way, but it's more expensive, is to run a separate experiment. I run a separate experiment and I do the validation on that separate experiment. There's a very nice paper by Bastos and Hagen on how to do that. Now when I've done that, I would take the separate data set and combine it back with the original data set. I'm not going to throw it away and rebuild an even better emulator, so it's not purely wasted, but it is a little bit expensive. So once I've got this emulator, what can I do with it? And there are probably more things than I've written down here, but the main things that I use it for: prediction, sensitivity analysis, uncertainty analysis, and inverse modeling. And I'm going to go through each in turn and explain the sort of things that we do with emulators. So the first one's prediction. So I want to run the model a place I've never run it before. Well, I can now predict with my emulator what that model would give. If you want to be very Bayesian, that's my belief about what the model is going to give me at this new position. And that has some uncertainty on it. So the great thing about an emulator compared to another interpolator, it gives you its own uncertainty. It tells you how well it's doing. So it might say you predicted somewhere and it's doing really badly, and you could do another model run to make sure that you compressed those uncertainties. So the uncertainties are sort of under our control, and I'll come back to that. And that prediction is essentially at no cost. So in building the emulator to do a prediction, we've gone from several hours on a high-performance computer to no time at all on my laptop. Now, some people say, oh, you've built me an emulator, I don't need my model anymore because I can predict with the emulator. That's not true. The emulator is a tool for understanding models. It's not a replacement. That's not what we build them for. So going up the sort of level of complexity, the next thing you might want to do is a sensitivity analysis. So my model has 20 input parameters. What does each one of them do to the output? If I change one a little bit, what does that do to the output? And importantly, what happens if I change two at a time? One at a time sensitivity analysis can be very misleading because these inputs often work together. We usually do one at a time and two at a time. We rarely get up to three at a time and four at a time because it gets really complicated, but we probably ought to. And there are what are called variance-based sensitivity measures, and there's a nice paper by Oakley and O'Hagan using emulators to build those sensitivity measures in a similar way to analysis of variance, to look at the one at a time, the main effects, and these interaction terms of how two parameters changing together will change that output. Sensitivity analysis is a great way to learn about your model. Then there's uncertainty analysis. If I'm uncertain about my inputs, I put some probability distribution on the inputs to my model. What probability distribution does that induce on the outputs? And in certain cases, we can do that analytically because our Gaussian process is as a normal distribution, and we can propagate that through. In most cases we can't do that, and often we use Monte Carlo. But Monte Carlo now is a bit different, because we're going to sample from the emulator, not from the original model. But we have to add this additional uncertainty because the emulator is not the model. It has this extra uncertainty part. But it's cheap. So before, when I had to do n runs to get the variance down, the cost was n times the cost of running the model. Now it's n times the cost to run the emulator, which is essentially free. So that cost is near zero. Doing 10,000, 100,000 runs is not a problem. There is, however, this additional error we've added in, the emulator error. The emulator isn't perfect. That's sometimes called the code uncertainty, but that's under our control, because when we do our training set, we can expand that training set and reduce that code uncertainty. In principle, we can reduce that to 0 if we do enough runs. Those cost, now the rule of thumb is 10 per input dimension to get a good emulator. I often get away with fewer than 10 per input dimension. Sometimes I have to use more. So Monte Carlo for uncertainty analysis becomes a much more entrancing prospect than trying to do it with the original model, when it's usually impossible. So far, I've talked about running the emulator in what's called forward mode. I have some property of the inputs, their distribution, their sensitivity, and I look at the outputs. But often, and in fact possibly more often than not with models, we're interested in taking something about the outputs, and make an inference about the inputs. So if I take some data, what can that tell me about the inputs to my model? If I go out and measure ocean temperatures, what can that tell me about the ocean viscosity value I've put inside my ocean model? That's called inverse modeling. And often it's about finding the best set of input values given the data, and we can then use those best set of input values to make predictions. And in different communities it's called different things. Sometimes it's called calibration. In the meteorological community it's often called tuning, inverse modeling, and there are probably other terms in other communities for this practice of collecting some real-world data, pushing it back through the model to tell us something about the model parameters, which we can then use to make future predictions. Now, there is an additional thing that now comes in. I said at the beginning our simulators are not perfect. The set of equations we have are not a perfect description of the real world. There are missing processes, some of which we know about, and even if we model those processes, the real world isn't a set of partial differential equations. So when we measure something, it's not, well, when we simulate something, it's not perfect, and it's not perfect when we measure it either. All our measurements are in error. So we're actually trying to balance or use some imperfect data to tell us something about imperfect simulators. Now, the difference between reality and the simulator or the model is known as the model discrepancy. And the way that statisticians set that up, the simulator is our black box, so it includes the difference between the numerical solution and the infinite dimensional analytical solution, which is the thing the applied mathematicians can get a handle on. And we confound that with the difference between the equations and reality. It's very important, though, to know that you're not getting a perfect answer, even if you could run it at that best set of inputs. And if you don't include discrepancy in your modeling, you will do what's called overfitting, where you fit your model to some of that discrepancy. You get a bad answer. There are wonderful examples of overfitting where you fit data noise, for instance. So you have to be very careful about the discrepancy. Now, Kennedy and O'Hagan, in a classic paper in 2001, put forward a really nice solution to this problem. They fit two Gaussian processes simultaneously. One's the emulator of the model, and the other is this discrepancy between the model and the data, and they take account of the data error. It's a really nice paper. The problem is that in practice, it's very hard to do that calculation because the emulator and discrepancy, you can swap things between the two of them and you can't tell. And in a follow-up paper, Brynjar's daughter and O'Hagan, they show that there's this what's called identifiability problem between these two parts, and one way around that is if you know a lot about the property of the discrepancy, or you know a lot about the property of the emulator and you can put strong priors on those, then you can solve this, but in general it's very hard to do. So what's an alternative? Well, an alternative is something that goes by the name of history matching, where we don't try to find the best inputs. Finding the best inputs is really hard. So what we try to do is to find really bad inputs, and that's quite easy to do. So we find where the inputs are bad, where the simulator is nowhere near reality, and we chop all those regions out, and hopefully when we've finished we've got a region where the simulator is good. We won't find the best, but we'll find regions where it's good. And we do that through calculating this implausibility. And we take the difference between the data, the prediction of the emulator at some point x, and we take the squared difference between those two, and we scale it by the data error, which we hopefully know, it's the measurement error, the emulator error, which is an output from the emulator, which is actually also a function of x, but I didn't put that in, and some discrepancy term that I'll talk a little bit more about later, which is a measure of how far we think the model is from reality. And if that value is large, and we tend to use 3, for reasons I can go into if you ask me later, that value of x is ruled out. And we proceed to do this in waves, so we do this once, then we compress down to the region, sometimes called the not ruled out yet region, and we then rebuild our emulator inside that region with some more model runs, rebuild it. This gets smaller because we've got a much better emulator. The ruled out region shrinks down again, and it shrinks down again until we stop. And two things will have happened. We stop when we can't rule out the space anymore. Doing more model runs doesn't help. We've got to the point where the data error and the discrepancy error here are dominating. This thing could go to 0. And then it might be this region is now small enough we don't care. It's somewhere in that region, that's fine. Or we could do a Kennedy-O'Hagan analysis in this small region. That's a lot easier than trying to do it en masse. And we could go and collect some more real-world data. Now, it could be that all of space is ruled out. This does happen. And that means that the simulator can't be made to agree with the data. So if I go back to this again, I've, in essence, taken this to 0, but this and this are so large that we can't get a fit between the model and the data. Now, we could do something about the data, or we could do something about that discrepancy term. It's probably that discrepancy term is too small. I think my model's much better than it is. Now, you could say, okay, I have to throw that model away, or we can have the discussion with the person who built the model. what tolerance to error are they prepared to have? How far from the data can that model be and still be a useful model? And that's quite a nice way to think about discrepancy. It's how bad can my model be and still produce useful outputs. So I'm going to give quite a quick example, because I'm running out of time, of some work I'm doing at the moment on diastolic heart failure. So diastolic heart failure affects about 450,000 people a year in the UK. And basically the heart gets stiff and has difficulty beating. Stiffness of the heart. There is no treatment. If you are diagnosed with diastolic heart failure, you get palliative care and that's it. It may be more than one condition. The people I'm working with think it is, and the reason there's no treatment is that treatments are for the different conditions. There have been 13 drug trials, and if there's 10 different diastolic heart diseases and each drug trial teaches one different one, they will all fail. And what we're looking at, can we use simulators fitted to individual patients to distinguish the ill from the healthy patients? And if we can do that, can we discriminate between different forms of diastolic heart disease and help clinicians come up with a treatment? So we have a cardiac model supplied by Steve Niederer at St Thomas's King's College. It models the shape of the heart during one beat. It takes about 6 hours to run. Your body does this a lot faster, but it takes about 6 hours to run on quite a fast Unix workstation. We're going to look at 20 input parameters. There are many thousands of outputs, and you'll see why in a second. So here's the model. So there's a grid on here, and we also have lots of time steps during that beat. So we have many thousands of outputs. So to build the emulator, the first thing we have to do is something I've not talked about before. We have to reduce the dimensionality of the output, and we use a clever variation on principal components, and we can talk about that later if you want. You probably want to talk to Danny Williamson, who's at the back, because he and his student worked this out. And then we emulate just the first few of those principal components, which give us an approximation to what the heart's doing. It's quite a good approximation. We have some issues with the model failing to complete. We push it in a parameter space where it gets so stiff it can't actually beat. And we have ways to deal with that, which we can talk about again if you want to. But once we've done these things, the emulators validate. We then get some data. This is a 3D MRI scan of someone's heart. I don't do this bit. The people at King's College do this bit. They identify the heart wall, and they then put a grid on there, and those grids points are in the same place as the grid on the model, and they supply us with an averaged heartbeat. The MRI scan goes, I think, over 10, 20 beats, something like that. And there's our data. So we have a single patient. We start off with this whole screen being the possible parameters, the possible x's, the inputs. We then shrink it down to wave 1. We do some more model runs within wave 1, shrink it down to wave 2. We do more model runs, and then we shrink it down and shrink it down and shrink it down. And that's traditional classical history matching. Now we have more than one patient. So this is the patient who's healthy, and this is the patient who has diastolic heart failure, and we're going to do history matching on both of them, and here I've put lots of patients, and we're going to separate them out into groups. And the hypothesis is if we get lots and lots of patients, we can separate them out in groups. The ones who are ill can be separated out into different groups, and we can start to say, well, this is a different sort of diastolic heart failure to this one. And because we're fitting these things to models, we can find out the biological reason why this one is different from this one. Whereas if you just did a cluster analysis on the MRI scans, you might be able to separate them out, but you wouldn't know why they were separated out. So there's additional gain from using a model. This is the result of the history matching, or one of the history matchings. It's a horribly difficult plot to look at because we're looking at 20-dimensional space. This is 20-dimensional geometry. Don't think too hard about 20-dimensional geometry. But the important thing is that blue here is where I can't rule out. I'm looking through the 20-dimensional, well, the 19-dimensional space, 18-dimensional space behind each of these little plots. And blue is where I can't rule things out. So this is the first wave, and I can rule some things out. This one here, this parameter here is quite clearly, this is the marginal, it's quite clearly pushed to this side. This parameter here is deterministic linked to this parameter, and we left that in because it's a nice sanity check, and we always get this straight line because they're basically the same parameter. I don't know why they gave it this like this, but it was quite useful to do because it showed we didn't screw that up. And then as we go down here, the blueness has disappeared in most cases, and we're starting to get a smaller region. But it's not a nice compact sphere like I did in my diagrams. It's some twisty thing in 20 dimensions. So it's very hard to visualize. So far we've only got patient data for 2 patients, one well and one unwell. Initially we talked to the modelers and the clinicians, and they weren't prepared to give us a discrepancy. So we set it to 0, and if you do that, the model just doesn't fit. So we went back to them and explained what we were doing in a little more detail and showed them the results, and they said, yes, but the model has a hard boundary at the top, so it's not a terribly good model. So we changed that. And they gave us a discrepancy, and with a more realistic tolerance to error, we get small regions for each patient that are separate. So we can separate the ill patient from the healthy patient. Now, we've only done 2 patients. We have to get a lot more patients and show that we can separate them into different groups. Finally, because my time's running out, very quick word about decision making under uncertainty. Jane's already mentioned this, so I don't have to go through it in any great detail. Catherine and I run a network called Models to Decisions about using models of the ones I've talked about to make decisions in the real world. We have a website, there are some brochures outside. Conclusion, statistical uncertainty quantification can be used to solve many problems. It's not a panacea, it's not trivial to do, but it might help in a lot of cases. There are lots of open issues. High dimensionality is a problem. We don't scale terribly well to very high dimensions. Discrepancy is still a problem for us, and it's a problem for everybody, how you handle discrepancy in a sensible way. We're working with applied maths on the program. We're starting to do some comparisons. When is the applied maths way of doing it better than the way that I do it, and vice versa. And we're developing some hybrid and some new methods. And I will finish there because I'm starting to eat into Catherine's time. So, thank you. Is there a quick question while we swap over computers? Yes?
So, interested in the inverse problem that you mentioned there as well, because I think one of the things you skipped over is that the inverse solution is non-unique.
Yes.
I was wondering...
Well, it can be.
Well, often it ends up being non-unique.
Yeah.
If we were to use the history matching aspect, could we then isolate different areas?
Yes. There's no reason that the history matching is going to give you a nice simply connected sphere. It can give you different blobs in different places. So if you do have 2 completely different solutions, it should show that up. Yeah, that's one of its advantages. Because you don't look for the best, you find good, and good can be scattered anywhere.